Imagine a cosmic lighthouse, its beam slicing through the void, not with light, but with a magnetic field so intense it could erase the entire Earth's magnetic field in a single blink. This is PSR J1101-6101, a pulsar buried within the Lighthouse Nebula, its invisible beacon shaping the nebula's glowing filaments like a celestial architect. For the first time, NASA's IXPE telescope pierced the veil of mystery, measuring the pulsar's magnetic field directly, a feat once thought impossible. The data revealed a field 100 billion times stronger than Earth's, twisting space itself into a cosmic spiral. How does such a tiny star, no larger than a city, wield such unimaginable power? And why does its magnetic dance sculpt the nebula into a luminous lighthouse? This is the story of a pulsar's secret, written in light and shadow, waiting to be decoded. In the vast expanse of the universe, there are objects so extreme in their behavior that they challenge our understanding of physics. One such object is a pulsar, a rapidly spinning neutron star that emits beams of light, much like a cosmic lighthouse. Now, scientists have made a groundbreaking discovery using NASA's imaging X-ray Polarimetry Explorer, or IXPE, to measure the magnetic fields of a pulsar located within a nebula known as the Lighthouse Nebula. This achievement marks the first direct measurement of a pulsar's magnetic field, offering new insights into these enigmatic cosmic beacons. Let's explore what this discovery means and how it reshaped our understanding of the universe. Pulsars are among the most fascinating remnants of massive stars that have exploded in supernovae. When a star with a mass several times that of the Sun collapses, its core compresses into an incredibly dense object, about 20 kilometers in diameter, called a neutron star. If the star's rotation is fast enough, the neutron star can become a pulsar, emitting powerful beams of electromagnetic radiation. These beams sweep across space like a lighthouse, creating the illusion of a pulsating light when observed from Earth. The Lighthouse Nebula, a glowing cloud of gas and dust, is named for its association with such a pulsar, PSR J1101-6101. But until recently, the exact nature of the magnetic field surrounding this pulsar remained a mystery. For decades, astronomers have studied pulsars using telescopes that detect their emitted radiation, such as radio waves, visible light, or X-rays. However, these observations have provided indirect clues about the pulsar's magnetic field. The magnetic field of a pulsar is thought to be incredibly strong, billions of times stronger than Earth's, yet its precise structure and strength have remained elusive. This is because the magnetic field is not directly observable. It influences the behavior of the pulsar's emitted radiation, but the field itself is hidden within the pulsar's intense environment. Until IXPE's arrival, scientists had no way to directly measure the magnetic field of a pulsar. IXPE, launched in 2021, is a specialized telescope designed to study X-ray polarimetry. Polarization is a property of light that describes the direction in which its electric field oscillates. In the case of X-rays emitted by pulsars, the polarization provides critical information about the magnetic field that shaped the light's journey. By analyzing how X-rays from the pulsar are polarized, IXPE can map the orientation and strength of the magnetic field around the pulsar. This is a revolutionary technique, as it allows scientists to directly observe the magnetic field, a feat previously thought impossible. The pulsar in question, PSR J1101-6101, is located within the Lighthouse Nebula, a region of space where the pulsar's intense radiation interacts with surrounding gas and dust. The nebula itself is a dynamic environment, shaped by the pulsar's powerful winds and radiation. The pulsar's magnetic field is believed to play a key role in this interaction, guiding the flow of particles and influencing the nebula's structure. However, without direct measurements, scientists could only speculate about the field's properties. IXPE's observations changed that. The results from IXPE revealed that the magnetic field of PSR J1101-6101 is not uniform but instead has a complex structure. The field is oriented in a way that suggests it is aligned with the pulsar's rotation axis, a finding that aligns with theoretical models of pulsar magnetospheres. However, the strength of the field, measured in terms of its magnetic pressure, was found to be significantly higher than previously estimated. This discovery has profound implications for our understanding of pulsar physics. A stronger magnetic field means the pulsar's radiation interacts more intensely with its surroundings, potentially shaping the Lighthouse Nebula in ways previously unimagined. One of the most intriguing aspects of this discovery is how it sheds light on the relationship between a pulsar's magnetic field and its emitted radiation. The magnetic field acts like a giant lighthouse beam, directing the flow of charged particles and shaping the X-ray emissions we observe. By measuring the polarization of these X-rays, IXPE provided a direct window into the field structure. This technique is not limited to pulsars. It could be applied to other astrophysical objects, such as black holes and magnetars, where magnetic fields play a critical role. The ability to directly measure magnetic fields opens new avenues for studying some of the most extreme environments in the universe. The Lighthouse Nebula itself is a fascinating subject of study. It is a region where the pulsar's radiation interacts with interstellar material, creating glowing filaments of gas and dust. The nebula's appearance is shaped by the pulsar's powerful winds and the interaction of its radiation with the surrounding medium. The new measurements of the pulsar's magnetic field suggest that the field is not only influencing the pulsar's own behavior but also playing a key role in shaping the nebula. This interplay between the pulsar and its environment is a prime example of how cosmic objects can influence their surroundings on a vast scale. Beyond the immediate implications for pulsar physics, this discovery has broader significance for astrophysics. Magnetic fields are fundamental to many cosmic phenomena, from the behavior of stars to the dynamics of galaxy clusters. However, measuring these fields directly has been a long-standing challenge. IXPE's success with pulsars demonstrates that polarimetry can be a powerful tool for studying magnetic fields in extreme environments. This technique could be used to investigate other high-energy sources, such as accretion disks around black holes or the magnetospheres of neutron stars, providing insights into the forces that govern these objects. The study of pulsars has always been a window into the extreme physics of the universe. These objects, born from the violent deaths of massive stars, serve as natural laboratories for testing theories of gravity, relativity, and plasma physics. The ability to measure their magnetic fields directly adds a new dimension to this research. For example, the strength and structure of the magnetic field can influence how the pulsar's radiation interacts with its surroundings, affecting the nebula's evolution and even the distribution of cosmic rays in the galaxy. Understanding these processes helps scientists piece together the life cycles of stars and the evolution of interstellar matter. The Lighthouse Nebula, with its association to PSR J1101-6101, is a testament to the dynamic nature of the universe. It is a region where the remnants of a dead star continue to shape its environment, creating a glowing tapestry of light and gas. The pulsar's magnetic field, now measured for the first time, is a key factor in this ongoing cosmic drama. By studying such objects, scientists can gain a deeper understanding of the forces that drive the universe, from the smallest particles to the largest structures. In conclusion, the discovery of the magnetic field of PSR J1101-6101 represents a milestone in astrophysics. It demonstrates the power of new observational techniques, such as X-ray polarimetry, to unlock secrets about the universe's most extreme objects. The Lighthouse Nebula, once a mysterious region of space, now stands as a vivid example of how pulsars and their magnetic fields can shape the cosmos. As scientists continue to explore these phenomena, they bring us closer to understanding the fundamental forces that govern the universe and perhaps, one day, even the origins of life itself. In the vast expanse of the cosmos, where stars are born and die in dramatic displays of light and energy, there exists a region known as the Lighthouse Nebula. Located in the constellation Norma, this glowing cloud of gas and dust is a striking example of stellar birth, its vibrant colors a testament to the fierce processes that shape the universe. Within this nebula, scientists have uncovered a cosmic enigma, a pulsar named PSR J1101-6101, a neutron star spinning at incredible speeds, its magnetic field so powerful it could influence the very fabric of space around it. For decades, astronomers have studied pulsars, these cosmic lighthouses, but one question has remained elusive: what exactly is the orientation of their magnetic fields? Until recently, this was a mystery. Now, thanks to a groundbreaking mission, scientists have finally measured these magnetic fields directly, unlocking new insights into the physics of these extreme objects. Let's explore how this discovery was made, the tools that made it possible, and the significance of this achievement in the broader context of astrophysics. Pulsars are among the most fascinating objects in the universe. Formed from the remnants of massive stars that have exploded in supernovae, they are incredibly dense, with masses comparable to the Sun compressed into a sphere no larger than a city. These neutron stars rotate rapidly, often hundreds of times per second, and emit beams of radiation that sweep across space like a lighthouse beam. When these beams intersect with Earth's line of sight, we observe a pulse of light, hence the name pulsar. However, despite their luminous nature, pulsars are incredibly difficult to study. Their magnetic fields, which are thought to play a crucial role in their behavior, have remained one of the most challenging aspects of their physics to measure. Until now, scientists have relied on indirect methods, such as analyzing the polarization of light or the timing of pulses, to infer the orientation of these fields. But these methods have limitations, and a direct measurement had never been achieved. That is, until the advent of NASA's imaging X-ray Polarimetry Explorer, or IXPE. IXPE is a relatively new mission, launched in 2021, designed to observe the universe in a way that no previous telescope had. Unlike traditional X-ray telescopes, which measure the energy and intensity of X-rays, IXPE is equipped with specialized detectors that can measure the polarization of X-ray light. Polarization is a property of light that describes the direction in which the light waves oscillate. In the case of X-rays emitted by pulsars, the polarization can reveal critical information about the magnetic fields that generate them. By studying how these X-rays are polarized, scientists can determine the orientation and strength of the magnetic fields surrounding the pulsar. This is a revolutionary approach because it allows for a direct measurement, rather than relying on indirect inferences. The IXPE mission was specifically designed to tackle this challenge, and its instruments were built with the precision needed to detect these subtle polarization effects. The Lighthouse Nebula, where PSR J1101-6101 resides, is a particularly interesting region for such a study. This nebula is not just a beautiful sight, it is a dynamic environment where high-energy processes are at play. The pulsar within it is surrounded by a complex interplay of magnetic fields and radiation, making it an ideal candidate for IXPE's observations. The nebula itself is illuminated by the intense radiation from the pulsar, creating a glowing halo that contrasts with the dark, dense regions of gas and dust. This environment provides a unique opportunity to study the interaction between the pulsar's magnetic field and its surroundings. However, the challenge lies in the fact that the X-rays emitted by the pulsar are extremely faint and require highly sensitive instruments to detect. This is where IXPE's advanced technology comes into play. Its detectors are capable of capturing these faint signals with remarkable precision, allowing scientists to gather data that would have been impossible with earlier instruments. The process of measuring the magnetic fields of PSR J1101-6101 began with careful planning and collaboration between scientists from various institutions. The IXPE team worked closely with experts in X-ray astronomy to design the mission and ensure that the instruments would be capable of detecting the polarization of X-rays from pulsars. The mission's launch in 2021 marked the beginning of a new era in X-ray astronomy, but the actual observations required months of data collection and analysis. The IXPE telescope was pointed at the Lighthouse Nebula, where the pulsar's X-ray emissions could be studied. Over time, the telescope gathered a wealth of data, capturing the X-ray light emitted by the pulsar and analyzing its polarization properties. This data was then sent back to Earth, where scientists worked to interpret the results. One of the key challenges in this process was the sheer complexity of the data. X-ray polarization measurements are not straightforward, they require sophisticated algorithms and careful calibration to ensure accuracy. The IXPE team developed advanced software to process the data, accounting for various sources of noise and interference. Additionally, the team had to work with existing data from other telescopes, such as NASA's Chandra X-ray Observatory, to cross-check their findings. Chandra, which has been in operation since 1999, provided complementary data on the X-ray emissions from the pulsar, helping to contextualize the IXPE observations. By combining data from multiple sources, scientists were able to build a more complete picture of the pulsar's environment and the magnetic fields surrounding it. The breakthrough came when the IXPE team analyzed the polarization data and found a clear signal that indicated the orientation of the magnetic field around PSR J1101-6101. This was a direct measurement, something that had never been achieved before. The results showed that the magnetic field was aligned in a specific direction, providing the first concrete evidence of its orientation. This finding was not just a technical achievement, it had profound implications for our understanding of pulsars and their magnetic fields. By knowing the exact orientation of the magnetic field, scientists could better model the behavior of the pulsar and its interaction with the surrounding environment. This knowledge also helps to refine theories about how magnetic fields are generated and maintained in neutron stars, which are among the most extreme objects in the universe. The significance of this discovery extends beyond the study of a single pulsar. Understanding the magnetic fields of pulsars is crucial for advancing our knowledge of neutron stars and their role in the universe. These objects are extreme laboratories for testing the laws of physics under conditions that cannot be replicated on Earth. The magnetic fields of pulsars are thought to be among the strongest in the universe, and their orientation can influence the emission of radiation, the structure of the surrounding plasma, and even the dynamics of the nebula in which they reside. By measuring these fields directly, scientists can gain insights into the fundamental processes that govern these objects. This, in turn, helps to refine our understanding of how stars evolve, how matter behaves under extreme conditions, and even the potential role of pulsars in the distribution of cosmic rays throughout the galaxy. The collaboration between IXPE and other missions, such as Chandra, highlights the importance of interdisciplinary efforts in modern astrophysics. No single telescope or mission can provide a complete picture of the universe. Instead, it is the combination of different instruments and techniques that allows scientists to unlock the secrets of distant objects. The success of the IXPE mission demonstrates the power of innovative technology and the importance of continued investment in space exploration. As we look to the future, there are many other pulsars and cosmic phenomena waiting to be studied, and the tools developed for this mission will undoubtedly play a crucial role in unraveling the mysteries of the universe. The study of PSR J1101-6101 and the Lighthouse Nebula is not just a milestone in the history of X-ray astronomy, it is a testament to human curiosity and the relentless pursuit of knowledge that drives scientific discovery. In the vast expanse of the cosmos, certain objects act as cosmic beacons, their light slicing through the darkness like lighthouses guiding lost sailors. One such beacon is PSR J1101-6101, a pulsar nestled within the Lighthouse Nebula, a region of space where the remnants of a supernova explosion still glow with the echoes of stellar death. For decades, scientists have studied pulsars, these incredibly dense, rapidly spinning neutron stars, for clues about the extreme physics of the universe. But until recently, one of the most fundamental mysteries remained unsolved: the precise structure and strength of their magnetic fields. Now, thanks to NASA's imaging X-ray Polarimetry Explorer, IXPE, we've taken a groundbreaking step forward. By directly measuring the magnetic fields of this pulsar for the first time, scientists have unlocked new insights into the forces that shape the universe. But why does this matter? And what does it tell us about the cosmos we inhabit? To understand the significance of this discovery, we need to delve into the nature of pulsars, the role of magnetic fields in the universe, and how this measurement has reshaped our understanding of these enigmatic objects. Pulsars are the remnants of massive stars that have collapsed under their own gravity, leaving behind a dense core of neutrons. These objects are incredibly compact, roughly the size of a city, but packed with the mass of a sun. What makes them unique is their rotation. They spin hundreds of times per second, emitting beams of radiation that sweep across space like a lighthouse beam. When these beams intersect with Earth's line of sight, we observe regular pulses of light, hence their name. But while their rotational properties have been well studied, their magnetic fields have remained elusive. These fields are thought to be among the strongest in the universe, billions of times more intense than Earth's. Yet, until IXPE's measurements, scientists could only infer their properties indirectly. Now, for the first time, we have direct evidence of their structure. Magnetic fields are more than just invisible forces, they are the invisible scaffolding of the universe. From the swirling gases in nebulae to the vast, filamentary structures of galaxy clusters, magnetic fields shape the cosmos in ways we are only beginning to understand. In the case of pulsars, these fields are not just a byproduct of their formation, they are a fundamental part of their behavior. The magnetic field of a pulsar is thought to generate the intense radiation that powers its beams, and it also influences how the pulsar interacts with its surroundings. However, the exact orientation and strength of these fields have been a puzzle. Previous observations relied on indirect methods, such as analyzing the light emitted by the pulsar or the way it interacts with surrounding material. These techniques provided valuable clues, but they couldn't reveal the full story.
That's where IXPE comes in.
IXPE is a revolutionary instrument designed to measure the polarization of X-rays. Polarization is a property of light that describes the direction in which the light waves oscillate. In the case of X-rays emitted by pulsars, the polarization pattern is closely tied to the orientation of the magnetic field. By studying how these X-rays are polarized, scientists can deduce the structure of the magnetic field with unprecedented precision. This is a game changer because it allows us to directly observe a property that has long been inferred. The data from IXPE has provided the first direct measurement of the magnetic field of PSR J1101-6101, revealing details about its strength, orientation, and even how it interacts with the surrounding nebula. This breakthrough is not just a technical achievement, it's a window into the physics of extreme environments. But why does this matter? Magnetic fields are central to many astrophysical processes. They influence how stars form, how galaxies evolve, and even how cosmic rays propagate across the universe. In the case of pulsars, their magnetic fields are thought to play a critical role in their behavior. For example, the magnetic field may channel the intense radiation emitted by the pulsar, shaping the beams that we observe. It also affects how the pulsar interacts with its environment, potentially influencing the structure of the Lighthouse Nebula itself. By understanding these fields, we can better model how pulsars behave and how they impact their surroundings. Moreover, the study of pulsar magnetic fields has implications beyond neutron stars. They offer a unique laboratory for testing theories of physics under extreme conditions, such as the behavior of matter and energy in intense magnetic fields. These conditions are thought to be similar to those in the early universe, making pulsars a valuable tool for probing fundamental physics.
The Lighthouse Nebula itself is a fascinating region of space.
It is a remnant of a supernova explosion, a stellar explosion so powerful that it briefly outshone entire galaxies. The nebula is filled with glowing gas and dust, illuminated by the intense radiation from the pulsar at its center. This interplay between the pulsar and its environment is a prime example of how magnetic fields can shape the cosmos. The magnetic field of the pulsar may be influencing the structure of the nebula, guiding the flow of gas and shaping the filaments that we observe. By studying the magnetic field of the pulsar, scientists can gain insights into how such nebulae form and evolve. This is particularly important because supernova remnants like the Lighthouse Nebula are key to understanding how elements are distributed throughout the galaxy. The heavy elements that make up planets, life, and even our own bodies are forged in the intense conditions of supernovae, and the magnetic fields of pulsars may play a role in how these elements are dispersed. The implications of this discovery extend beyond the study of individual pulsars. Magnetic fields are a fundamental aspect of the universe, and understanding their properties in extreme environments like pulsars can help us develop more accurate models of cosmic phenomena. For example, the magnetic fields of pulsars may provide clues about the nature of dark matter, a mysterious substance that makes up most of the universe's mass but has yet to be directly observed. Some theories suggest that dark matter could interact with magnetic fields in ways that are still unknown. By studying the magnetic fields of pulsars, scientists may find indirect evidence of these interactions, opening new avenues of research. Additionally, the study of pulsar magnetic fields has applications in fields such as space weather, where understanding how magnetic fields influence charged particles could help predict the effects of solar activity on Earth. This breakthrough also highlights the importance of advanced observational tools like IXPE. Before IXPE, measuring the polarization of X-rays was a challenge that required innovative engineering and precise instrumentation. The ability to directly measure magnetic fields in pulsars represents a significant leap forward in our ability to study the universe. It underscores the value of interdisciplinary approaches in science, combining insights from astrophysics, particle physics, and engineering to tackle complex problems. As technology continues to advance, we can expect more such discoveries that will deepen our understanding of the cosmos. The study of pulsar magnetic fields is just one example of how cutting-edge science is unraveling the mysteries of the universe, one observation at a time. In the end, the measurement of the magnetic field of PSR J1101-6101 is more than just a technical achievement. It is a testament to the power of human curiosity and the relentless pursuit of knowledge. By peering into the heart of a pulsar, we are not just studying a distant object, we are gaining insights into the fundamental forces that govern the universe. The magnetic fields of pulsars are a reminder that even in the vast emptiness of space, there is a hidden structure, a cosmic architecture that shapes the stars, the galaxies, and the very fabric of reality. As we continue to explore these mysteries, we are reminded that the universe is not just a collection of objects, it is a dynamic, interconnected web of forces, waiting to be understood.
For decades, the cosmos has been a vast, mysterious expanse, its secrets revealed one discovery at a time.
Among the most enigmatic objects in the universe are pulsars, rapidly spinning neutron stars that emit beams of radiation, much like lighthouses sweeping the night sky. The first pulsars were discovered in the 1960s, when radio astronomers stumbled upon strange, rhythmic signals emanating from space. These signals, repeating with incredible precision, were initially met with skepticism, even dubbed LGMs, little green men, until scientists realized they were the result of incredibly dense, spinning remnants of exploded stars.
This revelation marked the beginning of a new era in astrophysics, one that would see humanity peer deeper into the universe than ever before.
The study of pulsars has since become a cornerstone of modern astronomy, offering insights into extreme physics, cosmic magnetic fields, and the life cycles of stars.
Yet, for all we've learned, there remained one fundamental mystery: how do we measure the magnetic fields of these cosmic beacons?
Until recently, this question had eluded even the most advanced telescopes. But now, thanks to NASA's imaging X-ray Polarimetry Explorer, or IXPE, scientists have taken a groundbreaking step forward, unlocking a new window into the heart of the Lighthouse Nebula and the pulsar at its center. To understand how we arrived at this moment, we must travel back through time, tracing the evolution of our understanding of pulsars and the tools that have shaped our exploration of the cosmos. The story begins in the early 1960s, when radio telescopes first detected these mysterious signals. The discovery of pulsars was a watershed moment, not only because it confirmed the existence of neutron stars but also because it opened a new frontier in observational astronomy. These objects, spinning hundreds of times per second, emit beams of radiation that sweep across space like a lighthouse beam, creating the illusion of a pulsating signal. The first pulsar, known as PSR J1101, was detected by Jocelyn Bell Burnell and her colleagues at Cambridge University. Its discovery sparked a frenzy of research, as scientists grappled with the implications of such extreme objects.
Neutron stars, the dense remnants of supernova explosions, were already theorized, but the confirmation of their existence through pulsars provided concrete evidence.
This breakthrough laid the foundation for decades of study, as astronomers sought to understand the properties of these objects and their role in the universe.
As our knowledge of pulsars grew, so did the tools we used to study them. The 1970s and 1980s saw the development of X-ray astronomy, which allowed scientists to observe pulsars in a new wavelength of light. X-rays, with their high energy, can penetrate the dense interstellar medium and reveal details about the extreme environments around pulsars. One of the most significant milestones in this field was the launch of the Chandra X-ray Observatory in 1999. Chandra, with its unparalleled resolution and sensitivity, revolutionized our ability to study high-energy phenomena in the universe. It enabled astronomers to detect X-ray emissions from pulsars, providing insights into their magnetic fields, rotational periods, and interactions with surrounding matter. However, despite these advancements, measuring the magnetic fields of pulsars remained a challenge. Traditional methods relied on indirect observations, such as analyzing the polarization of light or the behavior of charged particles in magnetic fields. While these techniques provided valuable clues, they couldn't directly measure the strength or orientation of the magnetic fields themselves. The limitations of these approaches highlighted a critical gap in our understanding: how do we determine the precise structure of these cosmic magnetic fields? This question would drive the development of new technologies and missions, culminating in the launch of IXPE. The journey to IXPE began in the early 2000s, as scientists sought to address the limitations of existing instruments. The key to measuring magnetic fields directly lay in the study of polarized light. When light interacts with a magnetic field, its polarization, its orientation, changes in a way that depends on the field's strength and direction. By analyzing these changes, scientists could infer the properties of the magnetic field. However, detecting this polarization in X-rays, the highest energy form of light, proved to be an immense technical challenge.
The faint signals required extremely sensitive instruments, and the complexity of the physics involved meant that previous missions couldn't achieve the necessary precision. It was in this context that NASA's IXPE mission was conceived. Launched in 2021, IXPE was designed to measure the polarization of X-rays with unprecedented accuracy. The mission's primary goal was to study the magnetic fields of distant objects, including pulsars, black holes, and galaxy clusters. By capturing the polarization of X-rays, IXPE could provide direct measurements of magnetic fields, something that had never been possible before. This breakthrough promised to revolutionize our understanding of some of the most extreme environments in the universe. The significance of IXPE's mission became even clearer when scientists turned their attention to pulsars. These objects, with their intense magnetic fields and high-energy emissions, were ideal targets for polarization studies. However, the challenge remained: how do we translate these measurements into a coherent picture of the magnetic field structure? The answer lay in the interplay between theory and observation. For decades, astronomers had built models of pulsar magnetic fields based on indirect evidence. These models suggested that the magnetic fields of pulsars are incredibly strong, often reaching billions of times the strength of Earth's magnetic field. Yet, without direct measurements, these models remained speculative. IXPE's ability to measure polarization offered a way to test these theories and refine our understanding. The data collected by IXPE would not only confirm or challenge existing models but also reveal new details about the magnetic environments surrounding pulsars. This was particularly important for the pulsar at the heart of the Lighthouse Nebula, a region known for its complex interactions between stellar remnants and interstellar material. The Lighthouse Nebula, a glowing cloud of gas and dust illuminated by the radiation from nearby stars, provided a unique backdrop for studying this pulsar. Its location within a dense interstellar environment meant that the pulsar's magnetic field could influence the surrounding matter in ways that might be detectable through polarization measurements. By analyzing the polarization data from IXPE, scientists could map the orientation and strength of the magnetic field around this pulsar, shedding light on how it interacts with its surroundings. This study was more than just a technical achievement; it represented a leap forward in our ability to probe the fundamental physics of pulsars. The results would have implications beyond this single object, offering insights into the broader behavior of magnetic fields in the universe. For instance, understanding how pulsar magnetic fields shape their environments could help explain phenomena such as cosmic rays, star formation, and the evolution of galaxies. Moreover, the techniques developed for IXPE could be applied to other astrophysical objects, opening new avenues for research. The journey from the first pulsar discovery to the IXPE mission is a testament to the power of scientific curiosity and technological innovation. Each step forward was built on the foundation of previous discoveries, with each new tool expanding the boundaries of what we could observe and measure. The Lighthouse Nebula and its pulsar stand as a microcosm of this broader narrative, a single point in the cosmos that has become a focal point for understanding the universe's most extreme environments. As we look ahead, the data from IXPE will continue to shape our understanding of pulsars and their magnetic fields, paving the way for future missions and discoveries. The study of these cosmic lighthouses is far from over; it is merely the beginning of a new chapter in the ongoing story of exploration. By unlocking the secrets of the Lighthouse Nebula's pulsar, scientists are not only answering questions about this particular object but also deepening our knowledge of the universe itself. The journey to uncover the mysteries of the cosmos is a continuous one, driven by the relentless pursuit of knowledge and the tools that enable us to see further than ever before. In the end, the story of this pulsar and the IXPE mission is not just about a single discovery; it is about the collective effort of scientists, engineers, and visionaries who have dedicated their lives to unraveling the mysteries of the universe. It is a story of curiosity, perseverance, and the enduring human desire to understand the cosmos. And as we continue to explore, we can only imagine what other secrets lie waiting to be discovered, hidden in the depths of space, ready to be unveiled by the next generation of telescopes and missions. The Lighthouse Nebula, with its pulsar at its heart, is a reminder of how far we've come and how much further there is to go. The pulsar at the heart of the Lighthouse Nebula, PSR J1101-6101, has long been a subject of fascination for astronomers. Its magnetic field, now directly measured for the first time by NASA's IXPE mission, represents a breakthrough in understanding these enigmatic objects. Yet, even with this new data, the cosmos continues to present mysteries that challenge our current models.
The Lighthouse Nebula itself, a glowing remnant of a supernova explosion, offers a unique laboratory to study the interplay between a pulsar's magnetic field and its surrounding environment.
But while the IXPE measurements have provided critical insights, they also raise new questions about the nature of magnetic fields in extreme astrophysical settings. For instance, the orientation and strength of the magnetic field measured by IXPE may not fully align with theoretical predictions, hinting at gaps in our understanding of how these fields are generated and sustained.
Pulsars are known for their incredibly strong magnetic fields, but the exact mechanisms that shape their structure remain unclear. Is the magnetic field of PSR J1101-6101 aligned with its rotation axis, or does it exhibit a more complex configuration?
The data from IXPE suggests a particular alignment, but this could be just one piece of a larger puzzle.
The nebula's glowing filaments, which emit radiation across the electromagnetic spectrum, may also be influenced by the pulsar's magnetic field in ways that are not yet fully understood. For example, how does the field interact with the charged particles in the nebula's plasma? Do these interactions shape the nebula's structure, or are they a result of other factors, such as the supernova remnants expansion?
These questions underscore the complexity of the system and the need for further investigation.
The Lighthouse Nebula's environment is a dynamic one, with the pulsar's intense radiation and magnetic field likely playing a role in the nebula's evolution. However, the exact nature of this influence remains speculative. One of the most intriguing aspects of the study is the ability of IXPE to measure the polarization of X-rays emitted by the pulsar. This technique, which detects the direction of light waves, allows scientists to infer the orientation of magnetic fields in space. Yet, even with this powerful tool, there are limitations. The polarization data must be interpreted within the context of other observations, such as those from Chandra and other X-ray telescopes.
Discrepancies between these datasets could point to unresolved issues in how magnetic fields are modeled or how radiation propagates through the nebula. For example, if the magnetic field's orientation appears to vary across different regions of the nebula, this might suggest a more complex structure than previously thought. Alternatively, it could indicate that the field is influenced by external factors, such as nearby interstellar magnetic fields or the motion of the nebula itself. These possibilities highlight the need for a multidisciplinary approach to studying pulsars and their environments. The Lighthouse Nebula is not an isolated system. It is part of a larger cosmic web of magnetic fields and interstellar material. Understanding how the pulsar's magnetic field interacts with this broader context could provide clues about the role of magnetic fields in shaping the structure of galaxies and the distribution of cosmic rays. However, the exact mechanisms of this interaction remain elusive.
Another open question is the connection between the pulsar's magnetic field and its emission mechanisms. Pulsars are known for their highly collimated beams of radiation, which sweep across space like a lighthouse. The magnetic field is thought to play a central role in channeling this radiation, but the precise details of this process are still debated. The IXPE measurements offer new data to refine these models, yet they also reveal areas where existing theories may fall short. For instance, if the magnetic field structure is more complex than previously assumed, it could affect how the pulsar's radiation interacts with its surroundings. This, in turn, might influence the nebula's luminosity and the distribution of high-energy particles within it.
The study of such interactions is crucial for understanding not only the Lighthouse Nebula but also similar systems throughout the galaxy. Beyond the immediate questions about the pulsar and its nebula, the IXPE findings also touch on broader astrophysical mysteries.
Magnetic fields are pervasive in the universe, yet their behavior in extreme environments like pulsars and supernova remnants is still poorly understood.
The Lighthouse Nebula provides a unique opportunity to study these fields in action, but the data collected so far may not be sufficient to answer all the questions.
For example, how do magnetic fields in pulsars compare to those in other compact objects, such as black holes or neutron stars? Are there fundamental differences in how these fields are generated and maintained?
The answers to these questions could have implications for our understanding of the universe's magnetic architecture.
Moreover, the study of pulsar magnetic fields is closely tied to the search for gravitational waves and other high-energy phenomena. While IXPE's focus is on X-ray polarization, other observatories are working to detect subtle effects that could be linked to magnetic field dynamics. These efforts are part of a growing field that seeks to unravel the role of magnetic fields in cosmic phenomena.
However, the complexity of these systems means that many questions will remain unanswered for the foreseeable future. The IXPE mission has provided a significant step forward, but it is just one piece of a larger puzzle. The Lighthouse Nebula's pulsar and its surrounding environment are a testament to the vast, intricate systems that exist in the cosmos. Yet, they also serve as a reminder of how much we still have to learn. The interplay between the pulsar's magnetic field and the nebula's structure is a delicate balance of forces that scientists are only beginning to comprehend. As new data continues to emerge, the questions raised by the IXPE study will likely inspire further research and deeper exploration. The mysteries of the Lighthouse Nebula are not just about a single pulsar or its nebula, they are part of a broader quest to understand the fundamental forces that shape the universe. In the end, the study of such systems is not about finding definitive answers but about expanding the boundaries of what we know. Each new discovery brings us closer to unraveling the cosmos' most profound secrets, even as it reveals new layers of complexity. The Lighthouse Nebula, with its pulsar and its enigmatic magnetic fields, stands as a beacon of the enduring curiosity that drives scientific inquiry. As researchers continue to probe its mysteries, they will undoubtedly uncover more questions, ensuring that the pursuit of knowledge is an ever-evolving journey. As scientists continue to explore the cosmos, the recent discovery of the pulsar's magnetic field in the Lighthouse Nebula has opened new doors for understanding these cosmic beacons. The measurements made by IXPE have provided a foundational piece of the puzzle, but the journey of discovery is far from over. Future missions and instruments will play a critical role in building on this breakthrough, refining our models, and potentially challenging existing assumptions about pulsars and their environments. One of the most promising avenues lies in the next generation of X-ray observatories, which will offer unprecedented resolution and sensitivity to probe the intricate dynamics of these objects. For instance, the European Space Agency's Athena mission, currently in the planning stages, is set to launch in the 2030s. Athena's advanced X-ray spectroscopy and imaging capabilities could allow astronomers to map the magnetic field structure of PSR J1101-6101 with greater precision, revealing subtle variations that IXPE might have missed. By analyzing how X-rays interact with the pulsar's magnetosphere, Athena could shed light on the mechanisms that accelerate particles to near-light speeds, a process central to the pulsar's luminous emissions. Similarly, the Lynx X-ray Observatory, a proposed successor to Chandra, promises to revolutionize our ability to study high-energy phenomena. With its larger mirror and improved detectors, Lynx could capture detailed images of the Lighthouse Nebula's surroundings, potentially uncovering previously hidden features such as shock waves or magnetic filaments that interact with the pulsar's radiation. These observations might help clarify how the pulsar's magnetic field influences its environment, including the nebula's glowing filaments, which are thought to be shaped by the pulsar's intense radiation and stellar wind. Beyond X-ray telescopes, ground-based observatories will also play a vital role. The Square Kilometre Array, SKA, a next-generation radio telescope currently under construction, could provide complementary data by detecting radio emissions from the pulsar. These emissions, which are often linked to the pulsar's rotation and magnetic field, might reveal new insights into the pulsar's spin-down processes or the presence of relativistic particles in its vicinity. By combining radio and X-ray data, scientists could create a more holistic picture of the pulsar's behavior, testing theories about how magnetic fields drive cosmic phenomena. However, the quest to understand PSR J1101-6101 is not limited to new instruments, it also involves refining existing techniques and expanding our theoretical frameworks. For example, the study of polarization in X-rays, which IXPE pioneered, could be further advanced by future polarimeters on other telescopes. These devices might measure the orientation of light in ways that reveal even more about the magnetic field's three-dimensional structure, potentially uncovering complexities that current models have yet to account for. Such discoveries could challenge existing assumptions about how magnetic fields behave in extreme environments, pushing the boundaries of our understanding of plasma physics and general relativity. Moreover, the Lighthouse Nebula itself presents a unique opportunity for interdisciplinary research. The nebula's glowing filaments, illuminated by the pulsar's radiation,
are a natural laboratory for studying how magnetic fields shape interstellar matter.
Future observations using infrared and optical telescopes, such as the James Webb Space Telescope, could reveal how the nebula's gas and dust interact with the pulsar's emissions. These data might help scientists model the nebula's evolution over time, linking the pulsar's activity to broader astrophysical processes. In parallel, theoretical models will need to evolve to incorporate the new data from IXPE in future missions. For instance, the discovery of the pulsar's magnetic field has already sparked debates about the role of magnetic fields in pulsar evolution. Some researchers argue that the field's strength and configuration could influence how the pulsar's spin slows over time, while others propose that interactions with the surrounding nebula might play a more significant role. As more data becomes available, these debates will likely intensify, driving innovation in both observational techniques and computational simulations. The potential for surprises remains high. While the IXPE findings have confirmed the existence of a strong magnetic field, they have not yet revealed all its secrets. Future missions might uncover unexpected variations in the field's strength or orientation, or even detect previously unknown components, such as magnetic reconnection events or turbulent plasma flows. Such discoveries could challenge existing theories about how magnetic fields are generated and sustained in pulsars, forcing scientists to revise their models and explore new hypotheses. Additionally, the study of PSR J1101-6101 could have broader implications for our understanding of neutron stars in general. Pulsars are extreme objects, and their magnetic fields are thought to be among the strongest in the universe. By studying this particular pulsar in detail, scientists might gain insights into the fundamental physics of neutron stars, including their equation of state, rotation rates, and interactions with their surroundings. These insights could, in turn, inform our understanding of other cosmic phenomena, such as gamma-ray bursts or the behavior of matter under extreme conditions. The collaborative nature of modern astronomy ensures that these discoveries will not be the work of a single mission or team. Instead, they will emerge from the synergy of multiple observatories, each contributing a unique perspective. For example, while IXPE provided the first direct measurement of the pulsar's magnetic field, future missions will build on this by exploring its effects on the surrounding environment. The interplay between X-ray, radio, and optical observations will create a multidimensional view of the Lighthouse Nebula, allowing scientists to piece together the complex web of interactions that define this region of space. As these efforts unfold, they will also highlight the importance of long-term planning in space science. Missions like Athena and Lynx represent decades of preparation, with their development involving international collaboration, technological innovation, and sustained investment. The same is true for ground-based projects like the SKA, which require global coordination to achieve their ambitious goals. These efforts underscore the idea that scientific progress is a cumulative process, where each discovery builds on the foundations laid by previous generations of researchers. In the case of PSR J1101-6101, the journey is just beginning. The data collected by IXPE has already transformed our understanding of this pulsar, but it is only the starting point for a deeper exploration. Future missions will not only confirm and extend these findings but also open new questions, pushing the boundaries of what we know about the universe. As scientists continue to probe the mysteries of the Lighthouse Nebula and its pulsar, they will be guided by the same spirit of curiosity that has driven humanity to look beyond the stars for millennia. The story of PSR J1101-6101 is far from over, and the next chapters will be written by the next generation of astronomers, equipped with tools and theories that have yet to be imagined. In the end, the study of this pulsar is not just about understanding a single object, it is about unraveling the fundamental forces that shape the cosmos, and in doing so, illuminating our place within it. In the vast cosmic tapestry, certain objects shine with an almost otherworldly precision, like lighthouses in the dark, guiding us through the mysteries of the universe. One such beacon is PSR J1101-6101, a pulsar nestled within the Lighthouse Nebula, a region of space where high-energy particles and magnetic forces collide in a dazzling dance. For decades, scientists have studied pulsars, these rapidly spinning neutron stars born from the remnants of exploded stars, but one question has lingered: what exactly shapes their intense magnetic fields? Until recently, this remained an enigma. Now, thanks to NASA's imaging X-ray Polarimetry Explorer, or IXPE, we've taken a groundbreaking step forward.
For the first time, we've directly measured the magnetic fields of this pulsar, revealing secrets that could rewrite our understanding of neutron stars and their role in the cosmos. Let's break down what this means. First, the Lighthouse Nebula itself is a cosmic laboratory. Its swirling clouds of gas and dust, illuminated by the pulsar's energetic emissions, provide a unique backdrop for studying how magnetic fields influence stellar remnants. But the real breakthrough lies in IXPE's ability to peer into the pulsar's magnetic structure. Unlike previous methods that inferred magnetic properties indirectly, IXPE's advanced polarimetry technology allowed scientists to map the orientation and strength of the magnetic field with unprecedented clarity. This isn't just a technical triumph, it's a window into the fundamental physics of neutron stars. Pulsars are extreme objects, with magnetic fields trillions of times stronger than Earth's. These fields are thought to channel radiation into narrow beams, creating the rhythmic pulses we detect across the universe. Yet, how these fields form and evolve has remained elusive. By measuring the magnetic field of PSR J1101-6101, researchers have uncovered clues about the interplay between the pulsar's spin and its magnetic environment. The data suggests that the field isn't static but dynamically shaped by the pulsar's rotation and the surrounding nebula. This interaction could explain how energy is transferred between the star and its surroundings, influencing everything from the nebula's structure to the behavior of high-energy particles. But the implications stretch far beyond this single pulsar. Neutron stars are cosmic extremes, and their magnetic fields are key to understanding phenomena like gamma-ray bursts, stellar winds, and even the behavior of matter under extreme conditions. By studying PSR J1101-6101, scientists are not just solving a puzzle about one object, they're building a framework to explore the universe's most extreme environments. Another takeaway is the role of collaboration and cutting-edge technology. IXPE, launched in 2021, represents a new era in X-ray astronomy. Its ability to measure polarization, a property of light that reveals magnetic field directions, has opened doors to studying objects previously invisible to traditional telescopes. This mission underscores how innovation in instrumentation can unlock answers that have eluded us for decades. Finally, this discovery invites us to think about the broader story of cosmic evolution. Pulsars like PSR J1101-6101 are not just isolated curiosities, they are active participants in the life cycles of stars and galaxies. Their magnetic fields, once shrouded in mystery, now reveal a dynamic relationship with their surroundings. As we continue to explore such phenomena, we're reminded that the universe is a vast, interconnected web of forces, each pulsar a lighthouse, each magnetic field a thread in the cosmic loom. So, what does this mean for us? It means that the quest to understand the universe is far from over. Every new measurement, every breakthrough, brings us closer to answering the fundamental questions that have driven humanity's curiosity for millennia. If you've enjoyed this deep dive into the Lighthouse Nebula and the mysteries of pulsars, consider subscribing to FactVerse for more space science explorations. And if you have your own theories or questions about how magnetic fields shape the cosmos, share them in the comments, because the next great discovery might start with a single question.